Sir, is it clear now?
Little bit better than the last time.
Sir, can you check once again?
I think it is okay now. Can you increase the volume here? Can you say something, Ritesh?
Yes.
I think it is okay. There will be always delay problem. So it will not be as smooth as we are giving from here. So okay, I think you can carry on, Ritesh. Thank you.
Okay, sir. Okay. So, can you please confirm this time and you're able to see my screen? Okay. So, let me introduce this actually about the electric vehicle system. What actually we are doing. So here at VNIT, we are working on the power electronics and drives for the electric vehicle propulsion and charging infrastructure. And so some of the research area and the activities what we are carrying out is for the electric vehicle charging. In that we are working on the development of conductive chargers and wireless charging. And recently we handed over the technology to the industry for commercial application. Then in traction system, majorly we are working on permanent mode BLDC motor drive and fixed control. And then recently we developed our own synchronous inductance motor, non-permanent magnet wave. And then now we are working on the development of power electronics and control strategy for this synchronous inductance. And other than this, we are working on
Ritesh, I think if you switch off your camera, it will be better. Yeah.
okay. And then temperature regulation charging strategies, etc. we are doing. And then for the micro integrated application, we deployed 115 kilowatt wireless charge. Sorry, EV phase battery storage charging station in Godamara and Kodesha. And these are some one which are on the values of so, before starting, so maybe definition of an application. So, this definition what I'm solution is part of IEEE 2030. Okay. So, we can definitely read the definition here. But in general, if I want to define an electric vehicle, then we can say that is the final type of power in an electric vehicle is being delivered through an electric motor. Then that vehicle.
Excuse me, sir. Sir, your voice is not audible properly. They're unable to hear it clearly.
Just to answer. Um, Let me try with this. Actually, today our network problem is also there in issues. That could be one of the reasons. Just give me a minute. Hello. Sir, can you confirm this time it is okay? Hello.
Ritesh, you can start.
Now it is okay. Hello. Hello, sir.
Sir, you are audible.
Okay, thank you. Thank you. Okay, so to define electric vehicle, we just have to see that whether in any electric vehicle, in any vehicle, if the final tractive power is being delivered through an electric motor, then we will say that the vehicle is an electric vehicle. For us, this doesn't matter that from where we are receiving the energy. You can receive the energy from onboard IC engine, or you can receive the energy from onboard DC sources such as battery, fuel cell, photovoltaic panel. Then the question is arising, then why we are going for electric vehicle? Okay. reason for going for the electric vehicle is because you see that we have a traction motor there, and the dynamics of an electrical system is much faster than conventional mechanical system. So this is the one reason here that we get a better and faster dynamics. So this is not only a reason. The moment we go for the electric powertrain, then we get a flexibility of integrating multiple energy sources. So this is the main reason that why we are going for the uh, electrification of a vehicle. So when you are able to integrate multiple energy sources, then definitely we will be able to reduce the dependence upon one of the fuel, for example, petrol or diesel something. Okay, so we are going for electric vehicle with the fact that here it is a possibility to have a improved performance with reduced emission. So just to give you an example, let me draw one diagram. And so with that, I will be able to make you clear about the electric vehicle. So let me draw a conventional IC engine. So this is a fuel tank. Okay, this is a fuel tank, and to this IC engine is connected. IC engine, and this IC engine is coupled with a differential gear arrangement, different to the software, and then to this uh, here we are having wheels connected. So this is a typical case of a IC engine. From the efficiency point of view, we don't see that much improvement is there. Okay, that flexibility we get. How it is? Let us consider that same IC engine is there. IC engine is there, and then same IC engine there. But this time, we are doing that we are coupling this IC engine with a generator. Okay, so this generator is producing electricity. We have a power electronics converter which can convert AC to DC, and then here we get a DC bus. So let me write here DC. Now to do this DC bus, we have a motor controller. That is sometimes we say traction inverter also. So that motor controller, what it do, that it converts DC to AC, and then we can run a traction motor. So I'm writing only traction motor. And this traction motor is coupled with a differential gear. I'm writing DC here, differential gear. And then you have the. So this is a case you are observing in which only one motor is there, which is coupled with a differential gear, and to that wheels are connected, so you are able to deliver the power through the differential gear. But in some cases, it is possible that this motor can directly be part of the motor itself. Okay. So in that case, you will have to use two inverters. Now, so you see that this was the arrangement here. This was the mechanical arrangement. It has some efficiency. And now what we are observing that we have replaced that part, and now we have electrified section from here to here. So it will have some efficiency and it will have some efficiency. So more or less, if you consider the efficiency, efficiency with this e-powertrain section will be a bit higher, very not much higher, but a bit higher than the mechanical arrangement. So, but where we get the benefit? We get a benefit here. You see that here we are having a common DC bus. To this common DC bus, we can integrate multiple energy sources. For an example, this is a battery pack. Okay, so we can integrate. Let me connect directly. We can connect to DC converter also. If multiple energy sources is there, then to make a proper energy management, we can connect. So one battery is there. So you see that two sources are there. If you want, here you can connect to the same DC bus. If you are willing to work with a fuel cell powered vehicle, so you can definitely connect a fuel cell, this common DC bus. If you want PV to be integrated, so this PV can be integrated. Okay, DC to DC to the same common DC bus. So these are the energy sources. If you want that to the to this powertrain, we want other sources such as power sources. So those can also be connected, like you see that ultra capacitor bank. ultra capacitor bank is there. Okay, so we can connect. If you want to connect a flywheel, this is ultra capacitor. This is PV. This is battery. If you want to connect a flywheel, then definitely you can connect a flywheel also here. DC, AC, the motor is there, and then this is the traction motor, and to the shaft of this motor, heavy high inertia disc is connected. So this is a flywheel. So this is your power source, ultra capacitor, motor with a high inertia disc. This is an element of flywheel. This is also power source. This is fuel cell is the energy source. Photovoltaic panel is the energy source. Battery is the energy source. So you see that how many energy sources or power sources or their combinations can be integrated to this. Basically, this type of powertrain of an electric vehicle, which is electrified now. So you see that this is the major advantage that we are going for the electrification of the vehicles. So now you see that you have these many number of energy sources. So if you want, you can take maximum energy from here. And then in that case, you can reduce the size of the IC engine. Okay. Reduce the, maybe you want to have even more, and then even you reduce the IC engine even lower. Okay. There's a possibility that there's a possibility that you don't use any IC engine. Just a moment. You don't use any IC engine like this one. So now what this arrangement you are observing is a case of a pure electric vehicle in which the major sources are onboard DC sources such as battery, fuel cell, okay, and photovoltaic panel. But their combination with power sources such as ultra capacitor and flywheels. So this arrangement, what you are at present seeing is a case of pure electric vehicle. Now, depending upon if you are using only battery in your vehicle, then it is a battery powered electric vehicle. If you are using fuel cell, then it will be a fuel cell fed battery electric vehicle. If you are using a PV panel, then it will be a PV fed electric vehicle. But the issue with fuel cell and PV fed is that fuel cell is that they have very high energy density. High energy density means, you remember that just I used the word energy source and power source. So meaning of energy source is what? Like they have the capability of delivering a nominal current for a longer duration of time. So you will be able to run your vehicle for a longer duration. And energy density is represented in kilowatt hour 1 kg. Okay. Then what is a power source? The power source, they have the capability of delivering very high current. Okay, as compared to these energy sources, but for a very short duration of time. So these power sources, ultra capacitor or flywheel, help us in improving the dynamic performance of the vehicle, such as acceleration or like regenerations, etc. taking place. So for those cases, these power sources can be. But with the help of power source, you cannot run your vehicle for long duration. Okay. So this is a case of pure electric vehicle. At the moment, like you see that you have IC engine, even smaller in size, then the vehicle is called hybrid. So this structure, what you're seeing, is a case of a hybrid electric vehicle, and this structure is a series hybrid electric vehicle. Anyone is having any doubt, then you can ask me right now. So I hope I am clear to you that what is an electric vehicle? If the final tractive power is being delivered through an electric motor, then it will be an electric vehicle. Okay. Second thing, why we are going for electric vehicles? We are going for electric vehicle because we want to improve the performance of the vehicle and at the same time reduce the emission. So maybe it will be a confusing term. So even though if someone asks me that why, so better we can say that here, in case of electric powertrain, we have a flexibility of working with or integrate using multiple energy sources because of the availability of the common DCs. So this is what the definition of an electric vehicle. Anyone is having any doubt, then you can ask me right now. So here's the definition. You can definitely read. Okay. So if we talk about the pure electric vehicle system, then you can see pure electric vehicle system. So it will have different subsystems. What are those subsystems? So like here we categorize all of the subsystem as traction system, in which you will have a traction motor, which could be an induction motor, PMSM machine, then SRM machine, it's not synchronous locomotive. Means you can have a solution of synchronous, asynchronous machine, then permanent magnet, non-permanent magnet. The traction system consists of a traction motor and a voltage system. And then what is there inside the supply system? It consists of energy sources for their combination with the power sources. Okay. The moment you use multiple energy sources, in that case, what happens that you will have to take the help of power electronics to make the appropriate power flow between among the from the different sources, from what to the different sources. Okay, so this is not only the reason. You see that the traction motors are designed for higher terminal voltage. Here the terminal voltage is higher, but these energy sources have like they are capable of delivering even a nominal current, which is required for the traction even at the lower terminal voltage. For an example, if you see a three-wheeler, you will find that 48-volt battery pack is there. So 12 volt, 4 number of batteries are connected. You can see this one. So if you want, you can use only 12-volt battery, and then you use a boost converter and bring the voltage level to higher. But when we work with only battery pack, and so you will see that we never use a boost converter or anything. We only go for series connections of the battery, series and parallel connections of the battery. And the voltage level will be what the terminal voltage of the motor is required. Okay. Then after we have control and monitoring system. You can see it's a responsibility. We all know that what a control system do. It takes the information of whole of the system through the sensors and then analyze it, and it makes your system to follow your reference, which could be speed reference or torque reference. Then, because you see that we are using onboard DC source, when you will run your vehicle, battery is going to discharge. So now what we have to do? We have to recharge the battery. So for that, we need a charging infrastructure. Okay. So this charging infrastructure can be a single charger, which is dedicated for your vehicle, or there can be possibility of a place where multiple charging points are available, where multiple vehicles can go and get the charge. So in case you are having a single charging charger for your vehicle, what you are using generally, so that keep it separate. Okay, this is a single charger for your vehicle. But the moment the multiple charging points will come, means like this is an example, like you see here. So here we have a degree-fed and battery energy storage assisted charging station. So this is a common DC bus, and then to this DC bus, maybe some auxiliary loads are connected. Maybe you want, like if vehicle is not getting charged, you want to submit energy to the grid. Okay, and then multiple vehicles can be charged. So this is a case of a charging system where multiple electric vehicles can receive energy from a small microgrid. Okay. Now, the question could be from your mind. I will discuss this later on also. Maybe some portions again we'll discuss later. The reason here you see that why we are not going for the microgrid. Energy to receive from the grid. Simple reason is that just an example I give you. Okay, at your home, maybe like you never use current more than 1 ampere. Okay, it's a rare. Sometimes you run mixer and maybe AC. In that case, you can consume more current, but that is not a regular practice. So in general, what happens generally we draw less than 1 ampere current. But in practice, what happens when you go to charge your vehicle, even the two-wheeler takes 5 ampere of current. And four-wheelers takes maximum 15 ampere of current. So can you see that at your home, we consider that 1 ampere current you are let's say typically you're drawing. So charging a vehicle means two-wheeler means you're drawing the energy of 6 houses continuously for maybe 3 hours, 4 hours, 5 hours, whatever the charging time is there. Okay, and normal generally at home we do normal charging. So for that time, we can say that we are drawing that much of current, so maybe 8 hours. Okay, so this 8 hours of this much of high current, it means what? One charger is consuming energy of 8 houses or 6 houses for a two-wheeler and 15 houses for three-wheeler for continuous 8 hours. So whole of the burden will be there on the grid transformer, etc., everything. So, and the grid instability issue definitely can be there because now the you are using more and more energy. And if you don't want to have that such type of issue, then you have to install a transformer, a grid transformer at your place, which has a higher kVA rating. Then only it will be possible of stabilization. Otherwise, it will be difficult. So that's why good practice is that you must have a solar installation and a battery energy storage assistance so that you can have a charging facility during the sun hour and off sun hour. Okay. So let us start one by one. These are some developments with what we carried out with our students. Here, this is a hydrogen power cycle. This car is a city electric car on which I worked during my PhD. This top photovoltaic panel is there, ultra capacitor is there, and then battery pack is there. So all the system. Okay, just to complete you that energy sources have high energy density, kilowatt hour per kg, and power sources have very high power density in watt per kg. So if you want to have a optimal performance from your drive, from your vehicle, then you must have the combination of both energy source as well as power source. So you see that in a vehicle, we are using energy source, this one, energy source, and then a power source. So when you do like this, then your vehicle supply system performance is as per your requirement. You will be able to run your vehicle for a longer duration of time, and at that same time, when you want to accelerate, you will have a better dynamics and improved life of the ride. So you see that in this vehicle, we have battery, ultra capacitor, and feedback. Ultra capacitor is bidirectional. We can submit and take also. So you see that bidirectional converter is connected. Photovoltaic one you can submit battery energy. So only this DC converter is used. Okay. So these are some examples you can see that. Okay. Now, when we talk about the charging infrastructure in the evening, there I will talk a lot on this one. So this is just for the sake of completion of the topic to start with. Yeah? We discussed this part. Let me go to another section. So whatever will be left, I will continue in the evening. So for that, you don't worry. Okay. So now, let me discuss about BLDC motor drive for light electric vehicle applications. So immediately here you see that we have written BLDC motor drive and we are saying light electric vehicle. So what is the relationship between them? Actually, this PM BLDC motor drive, they are available up to the capability of 2 kilowatt. Nowadays, some design improvement, etc. are there. So some over 5 kilowatt also. So these motors are typically, we can say, up to 2 kilowatt nominal power, and then peak power is 4 kilowatt. So this is the segment which is quite popular in light electric vehicle. Why? Because these BLDC motors or PMSM machines, they do not have field wicking because of the use of the non-permanent. I will explain you this. So what happens is that we mostly work in constant temperature, and where it can be in the city condition always constant temperature. But in city condition, generally we go with the light vehicles. Two-wheelers are there, three-wheelers are there. So all those things, and you need to have a frequent start and stop. So even with a case of four-wheeler also. So what happens, because all the time you have to stop and then start again, which is very frequent. So mostly you work in constant temperature. Okay, so this is where this speed reducing motor have better performance as compared to other motors. Okay, in the constant temperature. Okay, so let me go ahead. So if you really want to learn the BLDC motor or traction motor or synchronous lattice motor, then one book is there. I suggest you to use it. This is this one, where this PCGEEI. If you go through this book, you will have clear idea. Then we have IEEE proceedings. This is the older version which I am using. After that, also some improvement came. So, but if you follow this IEEE proceeding 2007, then they have nicely explained the different cases of the machines and the drives for electricity. Then in motor generators for traction applications, the review. In this, they have very nicely classified the different which motor is good for which segment, like this. Okay. Let me get it. Okay, so this definition I already explained you. Okay, this part also I explained you that different subsystems from activator. This also I saw you the pictures. Okay, come to the traction. So there are some criteria for a motor to classify as traction. You cannot take your the motor which is there at your home, which is being used as a pump, or a motor which is there for the fan. You cannot use it for to run your vehicle. So there are some criteria. Okay, let me explain you. So what are those criteria? If you see that first, that high torque and power density. To explain you this, let me draw here something. Suppose that we have a motor A and motor B. If we say that motor A is having high torque and power density, it means we are talking about its physical size. Maybe this motor is very small. Okay, as compared to motor B. To get the same power and torque. So A is having high torque and power density. Next is high starting torque for low speed and high speed, high power for the high speed person. So if you remember that those who are from electrical background, that if you draw the what we said, torque and then speed characteristic, then attractive load is something like this. Okay. So here this is when you stop, then you need higher torque to make your vehicle to run. Okay, this is the higher torque. This one. You have to overcome that one. This is a torque speed characteristic of a traction wheel. And when you increase the speed, then the windage is dominant. So that's why this is there. This is hyperbolic. So you need to overcome this torque always. Higher torque. So that's why we need a high starting torque. When you run for the low speed engine. This is the low speed engine. You can see. Yes. Now, when you work, then second thing is there that when you are going for cruising, you are on the highway and you're continuously driving your vehicle. So there we need high power. What is the meaning? Let me explain. Suppose that there's one motor. This is torque and this is speed. And you remember that this is the speed torque characteristic of motor. This is constant torque zone. Constant. And here it is constant power zone of operation. Clear? So suppose that you have a motor. This is constant torque zone, city condition. Constant power zone is for cruising, where the torque requirement is less. So please see that if we draw the constant power, this is power variation. This is for torque. The power will be something like this. And then you see, constant torque and power is vary because electrical power is equal to the power is tau m minus omega. And if you consider there is no losses, the shaft is transmitting, then it will be mechanical. Okay, so tau into omega. So during constant torque zone,
power is directly proportional to speed. When the speed increase, linear variation will be there. But in after the rated speed, constant power zone here, you see that P is constant, so tau m and omega m is constant. Okay, it's constant. So this is what? This is basically a hyperbolic curve. Okay. This is a hyperbolic curve. P equal to tau m omega. If P is constant, then they have to be very hyperbolic curve. So this is the P constant. Now, let me ask you some question. Suppose that this is first case. In this case, what happens that we are having one torque speed for, let's say, motor A. Let's say there's another motor B, another motor B, whose starting torque is high. Okay, starting torque is high. So for the low speed application, which motor you are going to operate? Going to prefer A or B? So definitely it is going to be B because it is having high starting torque. You remember that for every motor to run, there must be some minimum torque requirement. You must provide a torque which is more than the minimum load torque. Then only you will be able to run. So this is the case. So suppose that this is a motor. So in this, how much can be the maximum speed? Only this one we can go. Let's say omega m 1. But suppose that you are having a motor in which the constant power, what you are seeing being delivered by the motor during the cruising is a bit higher. For an example, let me make it in this one. Okay, let's say it is something like this. Having the same constant torque and torque, but constant power and torque is different. Torque is different. So let's say that this was A and this is B. So which is you are going to prefer? Definitely we will be preferring B. Having the speed torque electricity. Why? B? Because here it is possible that you can run your vehicle at higher speed during the cruising. Then wide speed range with a constant power operating range of 3 to 4. That's what it is saying. See, what you are observing here, this point, this is called rated speed. Okay, rated speed. So here it is saying that speed in the constant power zone. Let's say this is omega. Maximum speed what you can obtain. That and this is the rated speed. Let me make here W rated. So this omega m2 must be 3 to 4 times the rated speed. Rated speed means if it is the 1000 RPM motor at a rated voltage and current, then in constant power zone, it should be able to run with 3000 to 4000. Okay. Anyone is having any doubt? Okay. Efficiency, etc. It is a certain parameter you have to respect. Then intermittent overload capability, typically twice the rated capacity. So what happens that in the city condition you are stopping, then again you are starting. So when you start, you basically accelerate. You want to reach to the speed as soon as possible, constant speed. So you accelerate. So when you accelerate, at that time you need to deliver high current. So high current is what? You are delivering higher torque. So they are talking about this torque. So this torque during the acceleration must be 2 times higher than the when you run your vehicle normal. Okay. Then reliability and all those issues are always there. So they must be ensured. Anyone is having any doubt here? Please ask me. Okay. So I explained you that what are the candidates. Candidates are asynchronous motor and synchronous motor. Example of asynchronous motor is induction motor. Asynchronous and synchronous motor examples are synchronous motor one, permanent magnet synchronous machines, synchronous switch reluctance motor, and synchronous reluctance motor. So these are non-permanent magnet solutions. But the issue is that these permanent magnet machines are very, very compact because we use permanent magnet. Okay, let us see the traction motor over a PLDC motor. So what the motor you see and see, this is a PLDC motor. Okay, and hub motor. In this case, you see that motor is part of the wheel itself. Okay. This is a hub motor or wheel motor. So a traction system is what? A traction motor together with a voltage source inverter. Okay, this is a traction motor. Okay. Now, you remember that we say about synchronous motor and asynchronous motor. What is the difference between? In asynchronous motor, like induction motor, you give the supply motor starts rotating. Okay, but in this synchronous machine, you give the supply motor is not going to rotate unless you are synchronized with the rotating. Okay. Yeah. Now, so for a PLDC drive, what are the things? You have a PLDC motor, then you have some Hall sensor arrangements. Hall sensor arrangements are there to know where the rotor is. And then based on this information of the Hall states, we identify the switches, S1, S3, which switches to be operated. Because the three phase, so either it will be operated in 180-degree mode or 120 degree or synchronous mode. So you first select the switch, and based on your control arrangement, you modulate the required switch so that you can have a very, very speed application. So let's see something more. You see, this is a PMSM motor, a BLDC motor. So stator is there, and you see that these are the permanent. These are permanent. North, south, north, south, north, south. There. Okay. Please keep in mind that we have slotted permanent line. So when the time will come for the discussions, arc magnet, etc., at that time you please stop me and ask that why this segmentation is there. Okay. When you go inside, you please see that this is a stator winding and the Hall sensors are mounted on the stator. The thing is that we say that Hall sensor is 120-degree displaced, but this is not 120-degree displaced. Then what is the reason behind this? So please remember, there is a relationship of theta electrical and theta mechanical. Okay, so theta electrical is always larger than the theta mechanical. Means number of pole pair times. Number of pole pairs means what? Let's say that your motor is having 8 poles. Okay, 8 pole pairs. So how many number of poles are there? 16 poles, not south, not south. Okay, so suppose that we say that Hall sensor is displaced by 120 degrees, then in mechanical space, how much it is? This is theta m equal to theta electrical by number of pole pairs. Let's say this machine is 8 pole pair machine. Okay, so it is 8 pole. Let's say that electrical angle is, let's say how much we want? 120 degrees. This is 120 degrees. So it is 15 degrees. So you see that these Hall sensors are displaced by 15 degrees. 50 degrees. In mechanical space, so that's why you see that they are placed all together here. Anyone is having any doubt? Then here you can see this is the inverter and this is the interface designed by yourself. If you want to implement your control. Okay. The microcontroller. Now, then what are the classification? Okay, we are talking about so many things, but I didn't explain to you about this. Why the name is BLDC? Can you give me just 2 minutes time? I'm coming. Just give me 2 minutes time. Just a minute. नहीं मैडम अभी तो क्लास चल रहा है
Hello, Ritesh sir. Sir, your voice is not audible. Ritesh sir.
Hello, sir. Sir, we can't hear you, sir. Your voice is not audible, sir.
Sir, can you turn on your mic? I think mic is turned off. Uh,
Hello, sir. Hello. Hello, sir. Can you please confirm?
Yes, now it is your voice is coming.
What happened, sir? Okay. One second, I'm sharing. Okay. So here I was explaining this case. Huh? So one concentrated type is what? Once again, I repeat. Let's say that it is the case of a synchronous motor in which stator is a stator. This is stator winding, and here we have a rotor which is being excited by a DC source or external excitation is there. And this is done through the process. So if when you excite it with a DC, this uh, rotor turns into north and south pole, and so we get the rotor flux. Because the rotor flux is stationary in nature because of the DC supply, so it does not produce any EMF into the stator wire. But the moment we start rotating this rotor, now the variation, the flux linkage takes place in the stator winding. So the EMF. So the nature of this EMF is decided by how this winding is there. If it is distributed in nature like an induction motor, the back will be sinusoidal in nature. If this is concentrated type, just like a DC motor, then the nature of the back will be trapezoidal. So one concentrated type, I explained you that winding can be like this here. Okay, like this one. Okay, another example of concentrated type is better. Concentrated. Let's say that one winding is there. It will come here, then it will go. It will come here, then it will go here, then again it will come here, like this one. This one. You make the one. This is called phase A. And similarly, phase B will be something like this. So its winding will be something concentrated like this. Okay, so this is going to be phase B. And similarly for phase C, the winding will be like this. So this is also an example of concentrated. Okay. So when we have a concentrated type winding, back here, and when sinusoidal distributed type winding, then it is a sinusoidal back. Now, it is a motor. We have to produce a maximum torque for it. So for that purpose, what we have to do, we have to inject current in the stator winding IA, IB, and IC in such a way that these currents should be synchronized with the back EMF like this. If it is sinusoidal like this one, and if it is trapezoidal type, then it should be synchronized with a black top portion back like this one. So if you then we say that we are able to use the maximum torque. We need to move at the positions. So you see in this case, sinusoidal current is being distributed, it is injected, and in this case, it is square wave current injected. So if you see the torque in this case, it is just like a sinusoidal machine. So the name of this arrangement is it is first motor of AC type. This is a synchronous motor of DC type. A synchronous motor of DC type is
Excuse me, sir. It's not audible from your end.
Now, what we do that you see that now in case of PMS machine, now if you make this arrangement, suppose that this is stator, winding is same. It could be distributed type, it could be concentrated type. Same stator winding. Right. Okay. But this time what we do that we remove this external excitation. Now this is not there. So what will happen? Still it is going to produce the same flux. Fire. But you see that buses are not used here. Buses are not used. So this, if you're not using buses, and then now if you rotate this, still it is producing fire because you have this permanent magnet. Now if you rotate this motor, the same situation will be there. You will have sinusoidal back here, whatever is back. So now in this case, what is happening? This is called synchronous motor or brushless synchronous motor of DC type. This is brushless synchronous motor of DC type. But what we have used here is we have used a permanent magnet here. So the name is given permanent magnet brushless synchronous motor of DC type. This is permanent magnet brushless synchronous motor. So in past days, frequently people were saying permanent magnet brushless machine, permanent magnet brushless machine. Later on, people started saying that brushless AC machine means only brushless AC machine, and this is still people are saying brushless DC machine. So they say permanent magnet brushless AC machine or permanent magnet brushless DC machine from this nomenclature. Later on, what they did, that everyone dropped this permanent magnet. They started saying it is a BLDC motor, and this one is a BLDC. Okay, but PMS machine. But this is a sensible back. This is not BLDC motor is clear to you from where it is coming. So it's a like the name is given DC, so it is a brushless DC. This motor also you remember that this was P and then repeating the constant here. So please don't get confused. That what is a DC motor that is called PLDC motor. Okay, these BLDC motor are simple. Now, there are some classifications basically with the BLDC motors. So you see that suppose that we are having a shaft. This is a shaft. Shaft of the motor. Okay, shaft of the motor, and this is the. So we have two axes. One axis is X. This is axial. Okay, this is axial, and this one is radial. Means radial to shaft, axial to shaft. So if the flux passes, you see that this is there. So if you look from this side, what is there? This is appearing. So if you see that the flux link is radial, this is radial, huh? This is radial. See, radial to the shaft. So this is called radial field machine. If you see that flux is axial to the shaft, you see that this shaft axis, this shaft axis. So how the flux is moving? This is axial. Also, this is passing here. This is the axial movement basically. So this type of arrangement is called axial phase machine. Nowadays you would have seen this using PCB printed stator line like this. In YouTube or somewhere you would have seen this. So these are axial field machines. In permanent magnet machine, it is because you have used what we say permanent magnet, so field weakening zone is not possible because you cannot drop down the field. Okay, so then how we can do it? So in PMSM machine of radial field type, field weakening possibilities. But in case of axial machine, it is possible that you can vary this distance by using. So if you vary this distance, the field you can. That's a good feature we see in the axial field machine, axial flux machine or axial field machine. Okay, and this is like people are trying to explore it. Now, next is our linear field. So you see that one is stator, another one is rotor. In rotor also it is linear, and in stator also it is linear. Axial, both in stator and rotor. So this is called axial, linear field permanent magnet machine. Then based on the back EMF, I explained you if the back EMF is trapezoidal in nature, you see that this is the phase A, phase A back here. This one is phase B back here. Similar phase C. So this is trapezoidal type. So it's, we give the name P and B and C. If the back is sinusoidal, we say it is a P and B and C. Now, surface mounted machines. Basically, they are popular for the PMB. So this is what the magnet, what you're placing is on the surface. So this is called surface mounted. Second, you see that the magnets are on, but they are buried inside. You see, they're buried, but on the surface. So it is surface inside. So basically, PM is surface mounted motors. Like this is SPM motor. In short, is SPM motor. There was another example is IPM motor. So how they are different? Let's say that this is IPM motor. So this is our short. So magnets will be placed something like this. And then here you have a stator. So what's the difference? This is called IPM machine. Difference is that this motor, you cannot increase the speed to much larger extent. Why? There's a possibility that these magnets, okay, because they do not have any external mechanical support here also. But in this case, you see that magnets are buried inside of the motor. So you can go even much higher speed because they have mechanical support of the structure itself. So IPM machine, you can go for higher speed, but in SPM machine, you cannot go for higher speed. So that's why you see that IPM machines are what? They are your PMSM motors. PMSM motor means permanent magnet brushless AC motor. So they can go for a higher speed. So we have two segments. One is light vehicle segment, in which the motor torque requirement is 2 watt, so 2 Newton meter, and maximum is 4 Newton meter. Then after we have this PMSM or BLDC motor or PMSM motor, which can go up to 30-40 kilowatts. Okay. That's a mid-duty cycle or mid-duty vehicles. After that, you have only option of synchronous motor. Okay, like here we have seen this motor will be used. In field weakening, etc., everything is possible. You know? So up to 150 kilowatt, we go for this synchronous motor, not PMSM, synchronous motor. Okay. Beyond 150 kilowatt, we go for induction. There is no substitute for that. Sir, please let me know if the time is over, so I can continue in the next session. See these things. from the electrical structure point of view, means how the magnet is placed. So you see that in this case, we have 180-degree arc of the permanent magnet. Okay, 180-degree arc of the permanent magnet. So this is called 180-degree arc. In this case, stator winding, you see that they will be star connected. Winding will be star. And at a time, two phases are going to work. But another example is 120-degree arc magnet. You see that duration is 60, 60, 120 degree. So they are displaced like this. Now, they're placed like this. So this is called 120-degree. This is called degree arc magnet, and in this case, the winding will be delta. This is the difference. Now your question, you remember that I asked you to remember the question. Let me know that why it is segmented there. So maybe like if you make whole of this one, so from the manufacturer point of view or transportation point of view, there could be problem. But here you see that what you have seen there, the same one arc magnet was cutted into multiple pieces. It was cutted into multiple pieces. Similarly, this side. Multiple pieces. And you remember there, I said that north, south, north, south, north. So definitely because you cut it them into small pieces here. So what happened? But if still they are 180. So suppose that we take a bar magnet like this. This is north. If we cut, what will happen? So is it clear? If you piece, let's say that this segment we consider, and if we cut into two pieces, so what will happen? It was north, but now it becomes north. Let's say north and south. Okay. So south, north, south, north, like this. North, south, north, south, north, south. So that's why, like here, you see that in the first picture, what I explained to you is that segmentation is there. So that helps you in proper manufacturability and transportation. Everything is possible. So I hope it is clear that why with how that is 180 degree, even though they are small pieces. Okay. So when it is 180-degree arc magnet, we inject 120-degree current duration. So how is the back here? You see, the back here is something like this. Back here is something like this. It's something like this. So, and the current required to be injected is sigma I. This I'm just drawing only one phase, not for other phase. Then for other phase, let's say this is the phase. So the back here phase, something like this. We have seen. Like this. So the current for this is something like this. So this is 120-degree. Now, in case of 120-degree arc magnet, 120 arc magnet, the injected current in the winding will be of 180-degree. This is, you see, so here phase current IA, because here like this is there. So that what IA IDC, let's say this is phase A, IA, this is IB, and this one is IC. So this current we are saying that 180. Okay. 180. But if you look onto this current, line current, okay, this phase line current, then it will be again 120. So from control point of view, there is no difference. 180° or 120°. Okay. So what is basically our intention? Just a minute. Now, here you see, you remember that we had a, let's say, 180° arc magnet, we say that permanent surface mounted permanent magnet motor of 120° with 180° arc magnet. So in that case, winding is what? Winding is star connected. Okay. So because this is the winding, and now you have a rotor. Rotor is there, and you're rotating this rotor. So each of the winding will be having some back EMF. So you will have back EMF in the winding. So plus, plus, plus. This is EA, which is EB. This is EC. This is phase A. This is phase B. And this is phase C. So this one is 20. So motor can be represented by a R, and this winding is there, so definitely it will have some resistance. So we can place the resistance of it. So this motor can be represented by a PVC motor can be represented by R and E. Okay. And to inject the current, how we can do? We have to take the help of the inverter, so that we can push the current into the wire, to the proper current. So what is our requirement? Is remember that we have trapezoidal back here. This is for phase A. This is EA. This is EB, and this one EC. And then we, to get the maximum torque per ampere, we have to inject the current synchronized with the flat top portion of the motor. Okay, this is the flat top portion. This should be synchronized one. For each phase, the synchronization should be there. Then only it will be possible to have maximum torque per ampere. Okay, let us consider what is the flat portion value. What is this flat portion? I. So at a time, in this case, only two phases will be conducted. So this is E I. This is I. This is E, and this current is zero, so no power. So what is the power in phase A? This EA multiplied by IA plus EB IC plus EC. EB EC IC. This is the electrical power which is there. So what is EA? It is, what is IA? It is I. Then what is EB? It is minus I. Then what is EC? It is just. This is EC and this I. So if you see that minus I and this is minus E. So minus and plus what is I? 0. And what is E? That is some changing EC. So this part is 0. So we are left with EI plus EI, that is equal to twice EI. So this is the electrical power. And if you consider there is no loss in the shaft, then this will be what? Mechanical power, and that is going to be equal to tau into the current. And this, what is the value of this flat portion? That is just like a DC motor, the value of this flat portion will be what? E equal to K times motor speed. Okay, so substitute the value. So you can get the torque equal to 2 multiplied by K times omega m multiplied by I divided by omega m. Okay. I will just take more 10 minutes and then we'll discuss it later. Huh? So here you see that omega get cancelled, and so motor torque is equal to Ki. And you remember for a DC motor, how much is the motor torque? Torque equal to Ki. So this is one of the reasons that why this motor is also called BLDC. PC term is given. Okay, and so you see that torque we can get here, maximum torque. This is not possible. So what is our intention? Further, our intention is that we want to inject square wave current into the winding this motor. We want to inject square wave current. So we have to see that how we can do it, because ultimate objective is what? We have to inject current in 120 degree mode in 120 degree mode of operation, and that it should be synchronized with the flat top portion. Why we are saying 120 degree? Each is 30 degree. So the duration of this back EMF is what? 120 degree. Yeah, 120 degree. And so current to be injected for what? 120. Please remember these angles are electrical angles. Okay. So then we have to learn how to inject this current. Okay. So let me go ahead. Okay. So before going ahead, so now we have seen that we have an inverter. With the help of inverter, we can inject the current into the motor, and then motor will keep on rotating. So we have to understand that how this motor is working. Then only you will be able to control the motor, otherwise not possible. So you see that to understand that what we have done, that this is the motor. You see that 180 degree arc ring. This is replaced by a bar. Okay. Then we have the winding. You see that phase A winding, phase B winding, and phase C winding. So when let's say that only phase A winding is there. Okay. So this is going to produce its rotor. Okay. But we have to produce the torque. So how the torque is produces? There must be interaction of rotor flux and stator flux. So we have to produce the stator flux. Then only we can interact with this. Means we are injecting a current which is synchronized. This is the simple meaning. So you see that this is phase A is there. So this can be this will be producing what? Phi A. Phi A. Similarly, B is there. So this is going to produce phi B. Okay, C is there, so this is going to produce this C na CC is there, so phi C. So this flux is getting produced. So we have to think that how this can be produced. So you see that suppose that our requirement is this one, our requirement is this one. So can we consider that we are having an electromagnets? Yeah. Electromagnets north south, so it can give the flux in this direction. This is north and south, so we can get in this direction. This is north and south. So you can get in this direction. Okay. Now, the question arises that what we are going to do, that we are going to inject the current into this. So let me draw once again that same inverter diagram. I will not be drawing both. Yeah. So we have 3 legs. Okay, this is DC bus. Here current is 3 volt. Okay. So what we have to do? If you are turning on upper switch, this is 1, 3, 5, 2, 4, and 6. So what will happen? If you turn on the upper switch, current will go into the motor. So when it is going into the motor and to the upper switch, so the nature of the current is something like this. Okay. So it is when this is like this, the current magnitude is I. So we say that it is going to produce a positive flux. What you are seeing, phi A. Upper switch. But next time when the cycle comes, okay, and then we will be operating lower switch. So what will be the nature? It will be the direction of the current will be negative. So if you reverse the direction of current, at present this is the direction, so flux is in this direction. But if you reverse the direction of current, what will happen? This north will become south, and this south will become north. Okay, so this will change its direction. So this was phi B, so we can say that this is phi B minus if you change the direction. This was phi A, so when the negative is there, so we say that it will change its direction. So this is phi B minus. Similarly for phi C minus. So please remember, to get phi A plus, we have the phase A current should be positive, means upper switch should be on. To get phi A minus, this is minus, this one is the minus, we have to give the lower switch, means it should be minus A. I current in the same phase. Okay, stator flux. These are all the stator flux. This remember. So lower switch is to enter. Then only it is possible that that current that from the winding. This is the winding. This is the winding. So current will go inside. So you see that earlier current was coming in this direction. Now current is going in this direction, changing the direction. So flux will change. Stator flux. So this phi A, phi B, phi C, and phi A minus, phi B minus, and phi C minus. These are stator flux. Hello, ma'am. So this is the situation. Okay, how we produce the stator flux. Okay, let me go. So this section I will complete and then I will give you. Okay. Okay. Now you see that same arrangement is there. So here you see that when we were giving an excitation here like this, phase A current. So let me phase A current like this positive. So what was happening? That it was becoming north and this was becoming. See, please, this is like this. It goes here like this in this winding, and then it is coming out like this. You got it? Just like a DC motor. Okay, so you are giving a current which is entering from here and leaving from this. So north and south. Okay, so don't get confused. Okay. So here we have this situation. So what is the flux in this direction? But now in this case, you see that we have changed the direction of current. It's the direction of current. It was entering. It was now it is leaving. So it is minus I. This was plus I. This is 0. This is 0. So what will happen? This phi A is now in the reverse direction. Now, so same thing we do for all the. So you see that we have phi A, phi A, phi B, phi C. Phi A minus, phi B minus, phi C minus. So we have the different 6 flux vectors are available. Now, let me bring you to. So here, if you are here, for example, here, so this stator flux is what? This is the resultant of these two, phi A and phi B minus. Similarly, you see that this is the stator flux, so this is the resultant of this and this. So you see that this is. Similarly, here we have phi S, so this is the resultant of phi C minus and phi B minus. So this is the situation. Similarly, here we have phi B minus and phi A minus, so stator flux is like this. Similarly, here and here, here and here. So I know that in your mind something will be coming, but keep that in your mind. Because these are something which is related with the control studies. Some idea can definitely come to your mind. Okay, so let me show you last one here, how this motor is actually rotated. So you remember that, let me draw here 1, 2, 3. These are the switches. This is battery, right? This is 1, 3, 5, 2, 4, and 6. And this is the winding. Please remember, and that we are willing to inject the current which is synchronized with the flat up portion. So first is what? IA positive and IB. How IA positive is possible? Positive. Switch 1 is on, and IB is this one. This is B phase, this is A phase and C phase. So switch 6 is on. So this is positive current and this is negative current. So what the flux will produce? IA plus will produce phi A and IB minus will produce IS. So what is the flux? Stator flux. And what was the rotor flux? You remember? This is the rotor flux phi A. So this rotor will try to catch this, and it will go and get aligned with this stator flux. Stator, and you cannot change this position. It is kept locked. If you want to change this position, then you have to change the excitation. So now what we have done, you see, IA plus is same, but IC minus is there. So the current was IA plus. Now this current is not there. The current is from here, IC minus. So you see that this is IA plus and IC. So this is going to produce phi A plus, and this is going to produce plus phi C minus. So where is phi A? You see that this one. And which is phi C and this one. So what is the now new stator flux? This is there. So earlier motor was locked here. Now it will again move to this side to get it locked. You see that it is locked. Okay. So this process will keep continuing. IB plus IC minus. Okay. So you see, IB plus is miss. IB plus, IC minus is phi C minus. So now this is not there. IB plus is this one, and IC minus is there. So IB plus means, which is the phi B plus. So this is, you see, we have a phi B plus. Okay, and IC minus is phi C minus. Where is phi C minus? This one. So which is the stator flux? This one. So this rotor will try to move here, catch it, and get locked. You see, it's getting locked. So you see that by selecting the switches, you are trying to move this stator flux, and so rotor is catching that, following that stator flux, and your motor is on rotation. You see that? Okay, I will share this slide with you. Don't worry. So we keep it here, and the next we will learn that how to know that where the rotor is, and how to inject the current into the rotor. So we will directly start from there. Now we are now going more towards the control. Okay. So now I'm stopping here. You please go for a lunch. Have a nice lunch. And in the evening at 4:16 we will meet today. But at that time I will not discuss this. I will discuss charging infrastructure. Okay. Thank you for now. If you have any question, keep it for the evening.
Thank you, Professor Keshri, for giving a brief idea about onboard and off-board charging technologies, about different motors, their operating principles, their structural analysis like of SPM, PM, BLDC. I hope it will help our participants. So now it's time for lunch break. Again, we'll resume at 2:30 p.m. With Professor Deepak Runaki from IIT Madras. Thank you.
Thank you. Bye.